switch topics a little bit, and in this session we're talking about applications of data science to different domains, and my task is to tell you about all the work we've been doing in the space of economics and mechanism design in particular. So I'll start with a little overview of the kinds of questions we're looking at, and then I'll delve in some detail into one of these. So let's see. Okay, so what is mechanism design? This is basically optimization when you have many participants in your system that are exhibiting strategic behavior and that hold private information. For example, here are a few settings where we have a platform or a seller, and there are multiple customers and perhaps multiple providers that are interacting on this platform, and the platform has a number of different choices it can make, and it needs to take into account the preferences as well as the behavior of these different participants in order to figure out how best to do their optimization. And so what we're talking about here, as I said, is private input that different parties hold, and these are selfish parties with their own objectives, and they behave in a manner that optimizes their own objective. And one of the things that the optimizer or the platform does in order to solve for their optimization problem is to gather data through market analysis to make an informed decision in these contexts. And the prototypical problem we'll talk about in this talk is a seller that has many different items to sell or allocate and wants to maximize their revenue. And one of the problems that comes up in this context when you're gathering data and using it as input in your problem is that these data can be incomplete, they can be inaccurate, there might be contexts where they don't follow the standard models or the assumptions that go into proving theory, and those are the contexts that we want to address through our work. So let me give a few examples of this. So in a setting where sellers are trying to understand the market in order to price their items or sell their items in the best possible way, perhaps they have limited information about this market. They don't have a complete and completely accurate model of buyers' behavior in this market, but they have certain statistics. How well can they use these statistics in order to do perform their optimization in a robust fashion so that they achieve guarantees no matter how what the underlying distribution is? So that's one particular direction. Another direction we look at in our work is settings where buyers don't know their preferences, and perhaps they are purchasing something like an experience good, or they're making a purchase online where they don't have entire information about what this item is, and they discover their preferences as and when they acquire the item. A third context, as I just said, is settings where distributional assumptions that we might make in order to make the theory work don't necessarily hold. And finally, there are contexts where we have some lack of information and we can acquire this new information at a price. And then the question arises, how much is it reasonable to pay to acquire this information, and what pieces of information should we acquire in order to best solve the optimization problem at hand? Okay, so in this talk, I'm going to focus on this third component here. We'll talk about problems where the theory makes very strong assumptions on the underlying distribution, and the question we want to ask is, what if these assumptions don't hold true? I should say that I'm not really following the chat, so if there are any issues, please just interrupt me and speak up. Okay, so the settings I want to look at are revenue maximization problems in mechanism design. And one of the paradigms that has been dominant in this area for the last 20 years or so is called the simplicity versus optimality paradigm. And this is motivated by the observation that optimal mechanisms, specifically revenue optimal mechanisms, can be very complicated and are quite impractical for most purposes. So to give you an example, in many settings, and a revenue optimal mechanism will require the seller to sell lotteries on items and will make randomized allocations from these lotteries to the buyers. And we don't really see such mechanisms in practice, and for good reason, because people and individuals are not very good at reasoning about randomness. Okay, and so the question arises, if these optimal mechanisms are complicated and unreasonable for practice, what about simple mechanisms that can actually be implemented in practice? Can we prove that simple mechanisms achieve good performance? And so I have a few references here, but there's really a vast literature on proving that in many settings, simple mechanisms do achieve approximately optimal performance. I'm not going to define the term simple. It's really, it's in the eye of the beholder, and we will see an example or two in a little bit. Okay, so what is the issue here? The issue is that these simplicity versus optimality results and good bounds are only known under very strong assumptions. And to give you a little example, imagine there's a seller selling 2 items. It turns out that if we don't make any assumptions on how the buyer values these different items or how these values are distributed in the market, in fact, there's no mechanism that can be described with a finite number of bits that will achieve any finite approximation to the optimal revenue. We do know that if we can assume that the buyer's values for the 2 items are completely uncorrelated and they compose nicely over sets of items, under these kinds of assumptions, we can get good bounds on simplicity versus optimality. But in the absence of these assumptions, and in particular this independence assumption, we really cannot even get a finite bound. And so this I consider as a failure of theory. One of the goals of the theory is to inform practitioners of what kind of mechanism to implement in practice. And in this case, the theory provides no good guidance at all. And so in a series of works over the past few years, one thesis we have proposed is that the issue with the theory here is that the optimal revenue benchmark is too pessimistic, and we need to rethink what the right benchmark is. And finding the right benchmark can help us make progress towards this question of, what among the class of simple practical mechanisms, what is the right one to use in any particular situation. And this, a good benchmark would help us get that kind of finer understanding. So let me tell you what what the benchmark we proposed is. This is a smaller class of mechanisms that we call by many mechanisms, and I can describe this through an example. So imagine that we have a selling mechanism that is selling 2 different kinds of fruit, and the banana is priced at $1, the orange is priced at $2. But if someone wanted to buy the pair of them, this is priced at $5. Now, this is an exploitative mechanism because if someone wants to buy both the pieces of fruit, they could do better by buying each one individually. And this is the idea behind buy many mechanisms. These are mechanisms that allow the buyer to purchase multiple options off of the menu as opposed to just a single option. And so if the buyer here had a high enough value for both pieces of fruit together, they'd be able to acquire those for $3 as opposed to $5. Okay. And so by many mechanisms disallow these kinds of super additive pricings and therefore are a smaller class than all possible selling mechanisms. And we define the by many revenue as being the maximum revenue that any by many mechanism can obtain. Or one way of thinking about this is, this is the most revenue a seller can obtain if the buyer is allowed to visit the store multiple times and interact with the mechanism multiple times. Okay. And so this is the new benchmark we propose. We ask, well, given some particular market and some particular mechanism design setting, how well can we approximate the optimal by many revenue via a simple mechanism? Okay. And this property of by many mechanisms not having super additive prices, this might seem like a pretty small change to the mechanism design problem, but it turns out that it completely transforms the simplicity versus optimality question. And I want to emphasize here that this new benchmark, it's not making an assumption on the kind of market, meaning the buyer's preferences over different kinds of items or how much money they're willing to spend. Rather than we're making an assumption on the buyer's behavior in the sense that the buyer is allowed to buy multiple options off of the menu. So the high-level takeaway is that the simplicity versus optimality question is completely transformed. And here's a picture that briefly describes what's going on. So here I have three different kinds of solution concepts. So the optimal revenue is at the top, then by many revenue, the optimal by many revenue in the middle, and at the bottom I have what's called item pricing revenue. This is the most revenue a seller can obtain by individually pricing items. So every menu option is just an item coupled with a particular price, and the buyer can purchase any number of items at the sum of those prices. And as I said before, there are settings where the gap between the optimal revenue and something simple like item pricing can be unbounded. But it turns out that the gap between by many revenue and item pricing is no more than a factor that's logarithmic in the number of items. So for example, if we have 2 items, then there can be markets where the optimal revenue is unbounded. The item pricing revenue is bounded, so this gap is unbounded. But the gap between item pricing revenue and by many revenue is about a third, of about a factor of 3. Okay, a little smaller than that. Okay, so that's and we can obtain this this kind of bound on the gap without any assumptions whatsoever on how the values are distributed, how the values compose across different items, and so on. Okay, so what enables this kind of these kinds of bounds? What makes by many revenue and by many mechanisms so well behaved? Well, one aspect is that the mechanism can only price discriminate across different kinds of allocations it makes to the buyer to a very limited extent, because it cannot charge super additive prices. And a consequence of that is there's limited price discrimination the mechanism can do across different buyers in the market. So if there are 2 buyers and their preferences are very similar to each other, then surely these buyers could spend very different amounts in the mechanism. But if that's the case, then one of these buyers is not too important from the viewpoint of revenue for the mechanism. Okay, so these observations together limit the amount of price discrimination the mechanism can do, and this drives many of the results I'll tell you about. Okay, and finally, it turns out that item pricings provide the approximation I mentioned on the previous slide, because item pricings are additive functions, and they pointwise approximate subadditive functions. So this is another technical observation um, our work introduces to this area. Okay, so as I said, we introduced this new benchmark a few years back, and since then we've done a lot of work in trying to understand this benchmark and what kinds of results it enables. And in more recent work, some of which is joint work with Rojan Rezwan, who is one of the Encore students, so students supported by Encore, and some of this more recent work is supported by this institute. We have developed a much better understanding of different structured settings where we get improved approximations, even small constant factor approximations between by many revenue and simple mechanisms. And some of our new work extends these approximations to settings with multiple buyers where there's competition across different buyers. We can also obtain menu complexity bounds that have to do with how well can you achieve 99% of the optimal revenue as opposed to just, let's say, a third of the optimal revenue. What kind of mechanism can let you achieve a 99% approximation to the optimum? And it turns out that no finite mechanism can do this for the optimal revenue, but we can achieve finite bounds for the optimal by many revenue. So this is another kind of result that's enabled through this new benchmark. Finally, one interesting concept in mechanism design is that of revenue monotonicity. And the way to understand this is to ask, well, suppose the seller invests in the market through, let's say, advertising or other means, and brings about an improvement in the value buyers ascribe to the items the seller is selling. Does that mean that the seller's revenue will increase, or at least weekly increase? Will investment always lead to some weak increase in the seller's bottom line? And it turns out that for optimal revenue, this does not always happen, which is very counterintuitive. So it might happen that every buyer values every bundle of items more than they did before, and yet the optimal revenue is far, far smaller. In fact, an unbounded factor smaller than what it was before. This is one of the mysteries of revenue optimal mechanism design, and one of the reasons that this benchmark of optimal revenue is such a strange benchmark. And it turns out that for by many revenue, we can show that there's a kind of revenue continuity property that it satisfies. So it's much better behaved in this context. Okay, let me finish up. I'm nearly out of time. Let me mention a few different directions we're exploring as future work in this space. So the first one is to weaken the by many definition and try to understand to what extent the specifics of the model drive these results, and to what extent we can move the needle forward in relaxing these behavioral assumptions we make on part of the buyers. Extensions to other kinds of settings like two-sided markets and beyond the objective of revenue maximization. These are other directions we're thinking about. And then finally, just developing a better understanding of simple practical mechanisms. This is really the goal we were after in defining this benchmark. So other ways of developing this understanding, and also computationally efficient approaches to optimizing over these classes of mechanisms. These are very much directions with a lot of open questions, and these are some of the directions we're looking at currently. Thank you. I'll take questions. Are there any questions?
I have a question. I was just personally curious. Was there a particular application that was motivating this work?
So, I mean, applications of mechanism design in general apply to, a lot of pricing settings. So if you think about an online retailer like Amazon or Walmart, you could ask, well, how should they bundle items, or something like hotels.com, how should they, bundle their products, display their products, create assortments. These kinds of mechanism design questions are one component of those systems. And one challenge that the theory has is when we look at the space of all possible levers these platforms might have, the space is very large, and most of the objects in the space don't really make sense in practice. So Amazon is not going to sell you a lottery that'll give you, a good item with some probability and a poor item with some probability. And so it's from an application viewpoint that becomes quite meaningless. But in theory, the tools that we've had are optimizing over this large continuous space of all possible interactions or protocols the seller might use. And optimization over smaller spaces either requires motivating why that smaller space is reasonable. Like, for instance, why is item pricing the right thing to do and not some sort of bundling of items? You have to have some sound reason for selecting a particular smaller space. And then secondly, optimizing over such, uh, 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 discontinuous spaces of outcomes can also be computationally hard. So those are both reasons for which typically the theory considers the space of all possible mechanisms. And the point of this work is to give a sound basis for selecting specific classes of simple mechanisms to optimize over. So
Thank
hope that makes sense. Yeah.
That was really helpful. Thank you. Thank you very much.